All right, guys, let's get started with the second part of the lecture. And now we're going to be talking about model-based diagnosis. And you can think of this as the problem that is trying to answer basically what happened. Why did things go wrong? And as I mentioned, this was basically studied extensively, particularly in the 1980s. And there was a debate at that time of how to formulate this and what is the right answer to the question of what went wrong. And eventually it was settled after about a decade of trying various things out. And we will be illustrating this using a very simple type of systems, which are Boolean circuits. And that has been traditionally the domain used in these discussions and these initial papers, but actually it's not specific to that. You can think of systems that are made of components. So you could have, let's say, a block diagram where you've got inputs to components and there's something inside that produces an output that feeds to something else and so on. They really do not have to be logical gates. But this is concerning, in general, the notion of a system that is made up of components, and components have inputs generate output. And doesn't even have to be physical systems, what we're going to be talking about. It could be a system of beliefs where these guys are making inferences based on the inputs. So it's pretty more general than what our examples will suggest, but let's get going with this. We will be using these two circuits as illustrative examples throughout. And I'm going to start first by defining some basic notions here quickly. They're all intuitive to introduce some terminology, and then we would use it. So this is called a system. In this literature, if you look at the papers, it's going to say this is a system and this is a system. And there is the notion of basically a system description. And a system description is a knowledge base that describes how this system is supposed to behave. So if we look at this particular guy here, we just have two inverters. We number them 1 and 2, and we will say that this system has two components. So there is the notion of a component. And this is the description for that system. And what you see here is it has the following form. If OK1, if this component is OK, then this. Now, what is this? This is relating the input and output behavior of that component, basically saying the input or output will be different. It's declaring it as an inverter. All right. So this guy here, OK1, we call these the health variables. And these are variables where you have one for each component, and the idea is it captures the state of that component. And the idea is the component could be in different states, and its behavior will depend on which state it is in. In the simplest case, we simply use OK, which means OK, it's behaving normally, not OK is not behaving normally. All right. So we have health variables, and now we have a system description. And if you look at this particular system, it's described in two different ways. There's two different descriptions for it, this and that. And what's the difference between them? This is saying if the first component is OK, it behaves like this. If the second component is OK, it behaves like that. What's happening here? I have a little bit more. This guy is silent on what happens when the component is broken, right? Everything's possible. This guy is not silent on what happens when the component is broken. It is saying the same thing that the first guy is saying, which are these two guys here, this guy and that guy, but it's adding more, saying, by the way, when component 1 is not OK, it's broken, what happens? This is saying it either acts as a buffer instead of an inverter, or the output will always be 0. It will be stuck at 0. And it's doing the same thing for here. When you have this, we will say that we have fault models. Okay. Now, there is a chapter that we're going to distribute that discusses model-based diagnosis, and that has a lot of material. We were not going to cover it all, just a subset of it. And part of the material is what happens when you have fault models versus not. We're not going to get into this today, but if you're curious, you can check, because there are results that hold only if you have or not have fault models, but we're not going to get to these results. We're just going to focus on the basics today. Okay, so guys, we have the basic notions now. We have the notion of a system description, a component, a health variable, and now we're going to do a very simple question that we were going to ask, and then a more advanced one. All right. The very simple question is, I give you a system description and I give you what we call a system observation. So the system observation you can think of as basically asserting the value of some variables that are not health variables. So the idea is you can never observe the health variables, right? These you cannot observe. But in this case, you can observe A, potentially B and C. In this case, you can observe A, B, C, D, E. You would want to at least be able to observe the inputs and the outputs. And by the way, this is a more complex example, and this is a system description. So I'm going to ask you two questions. The first is a very simple question. I'm going to give you a system observation, and we want to know if it's normal or abnormal, all right? And you should be able to tell that. And then what we're going to do after this is I'm going to show you a system observation that is not normal. And meaning it contradicts the intended behavior of the system. And we're going to focus on one question. What happened? What is the explanation for an abnormal system behavior? And there we're going to get to the bottom of our results and what we're going to observe there. And you can see already, I'm saying, how do you explain an abnormal system behavior? You can see the word explain coming up there. Okay, guys, let me give you some simple system observations, and you guys just tell me whether these are normal or abnormal. So we're talking about the first guy now, and I'm going to give you two of them. Let's call this guy A and C, and let's call the second one is a system observation A and not C. So in this case, I observe that this is high and the output is high. And the question, normal or abnormal? And in this case, I observe that the input is high, but the output is low. Normal or abnormal? Based on intuition, just tell me. First guy, alpha 1, normal or abnormal? Okay. Some people already said abnormal. We're talking about alpha 1. Inverter. Is this guy normal or abnormal? People are saying not normal. Well, let's see. A is true. Inverter becomes false. Inverter becomes true. Right? It should be normal. And people actually adjusted that. That's good. Normal or abnormal? Second guy, alpha 2. Well, this guy. I put a high here and I got a low there. Normal or abnormal? And people are saying abnormal, right? Because if I put a high, this should be a low, this should be a high. So this is not normal. Okay, quick question. Give me a query that will produce this answer. You guys know now how to do logical reasoning. Tell me I need a box that does that and I need to figure out. So here's what we're going to do. We're going to call more generally the system description delta. We're going to call the system observation alpha. And now question, and give me something that you can pass to an algorithm. Now you're doing it based on intuition. Question is observation alpha normal. And what do we do? And right, so someone is saying, are we going to observe B? Let's assume now we're not observing B. So we have an observation, let's say about these two guys, it's alpha. The system description is delta. I want to write something here that can be evaluated by an algorithm. So it should be, well, let me make it simple on you. You have a SAT solver and you want to pass something to the SAT solver. And depending on what you get from the SAT solver, yes or no, you will know whether the observation is normal or not. What should you pass that SAT solver? What should I give the SAT solver? SAT, what should I give it? And someone say, give it the observation in this particular case. Not only the observation, right? I have the system description. I mean, whether an observation is good or bad depends on what kind of the system description. Okay, so people are saying give it delta and alpha and check whether that's satisfiable, whether this observation is consistent with delta. Let's see, will that do it, right? Okay, see, even that one is not immediately obvious. Well, here's the thing. What you really need to do to answer this question, this is not going to do it. This is not going to do it because this observation is consistent with the system description if, for example, the components are broken. So what you really need to say here is, in this case, is delta and alpha and OK1 and OK2, is this consistent? So given the system description and given the assumption that both components are working, is this behavior consistent with that? And what you will see in this case, you will get a yes, and in this case, you will get a no. So what you want to ask is this behavior of the system, as indicated by the system observation, is it consistent with the system description and the fact that all components are working properly, right? So if you put all of these things together and you pass it to a SAT solver, you're going to get either a yes or no. This would be normal. This would be abnormal. Okay. All right. So this is the simple question. This is not what we're after. This is pretty simple. Detecting whether something is normal or abnormal. We're interested in something a little bit more subtle. And I'm going to go ahead and now ask you a question about the second system, which is a little bit more involved. And this is going to be an abnormal behavior. I'm going to tell you up front, it will be an abnormal behavior. Let me remove this stuff here. And the question is, so we already know it's abnormal, and I want you to tell me, if someone were to ask you what happened here, what would you say? Okay. And this observation now is this guy, and it basically says not A and not B and not E. Okay, so I put a low, low, and I got a low. Well, let's see. If this is a low, this should be high under normal, if every component is working properly. Low gives me high, low gives me high, high and high, it's an OR gate, I should get a high, but I got a low, right? So this behavior is basically abnormal. The question is, and maybe some of you have done digital logic and played with these things. If I come and tell you what went wrong here, what would you say? How would you describe the problem, right? I mean, we know something is not functioning properly, because if everything's functioning properly, I shouldn't see this. When I put a low input A, low input B, I should get a high input, but I got a low. So something went wrong. And what people struggled with for a long time is, what do I say back, right? Okay, someone already wrote something here. Someone said, either both OK1 and OK2 are false, or OK3 is false. So here's a candidate. Someone basically wrote the following. So not OK1 and not OK2 or not OK3. This is interesting. I got a formula. Someone basically wrote back a formula, and said, when you tell me what went wrong here, this is my answer. A Boolean formula that says not OK3 or not OK1 or not OK. Do you guys agree with this? Anyone who actually think this is not a characterization of the situation? Do you see something wrong with it? I mean, it's really intuitively, it's saying either this guy broke or both of these broke at the same time. That's basically what it's saying. Okay, this is the correct answer. And we're going to eventually call this guy the health condition. So this is going to be the health condition of delta and alpha. So delta is the system description, and this is the system observation. So this is going to be denoted by health, delta, comma, alpha. Okay. The question is, okay, we had someone, and he looked at this, used intuition, and wrote this guy. What is this? Logically, how do I get it systematically? And effectively, that's what people went over for a very long time. And now I'm going to show you two definitions, the original definition and then a more succinct definition that we can come up with given the tools that we started in this class. So when people did this initially, they did not have as many tools as you guys already now have. And that will show you a fascinating example how researchers can spend years battling with a notion, but when they have the right abstraction, they can probably get to it directly. I'm going to show you next how to generate this guy and similar guys systematically using what people call the notion of a consistency-based diagnosis. Let's do it together, and you will be actually amazed how this works. So here's what we're going to do. We will define a notion of diagnosis, right? So it's this guy for basically system description delta and system observation alpha. And then we're going to use it to come up with that expression that we just talked about in a systematic way. The idea is pretty simple. The idea is that you look at the health variables, all right? And we call these in this case, OK1, OK2, and OK3. Now, if you look at these variables, every state of them defines what we call a state of the system or a health state, right? So there are all possible or 8 possible health states of the system, and I'm gonna enumerate them here, okay? And your goal or your role is to look at each one and tell me whether a particular state of these variables is consistent with the system description and the observation. And we're gonna do this on this side here. So remember, what we have is this system description. So we're talking about, in this case, for this guy, we're talking about delta B. That's this guy. We're dealing with this guy. And the observation that we have here is what we mentioned, not A, not B, not E, okay? Low, low, low. And the question is, I wanna go over each possible state of the system and say, is this consistent with the system description? And is it possible? Is it possible that the system can be in this state? So let's just do a couple of them quickly. And we're going to find out that those that are possible, we will call them a diagnosis. So 8 of them. Let me look at the first guy. OK1, OK2, OK3. Is this possible? Not possible, right? Given this system description and given this observation. So this is no, that is not possible, okay? And here we're going to write, is it a diagnosis for delta B and alpha, right? So no, it's not a diagnosis. A diagnosis has to be a possible health state. This is not possible. What about the second one? Quickly, the second one, is it possible or not? And someone is saying, yes, it is possible. So this is possible, right? This is where both of these guys are properly functioning, but this is improperly functioning. Yeah, it's possible that this can happen. Okay, you can go and do the rest. And what you'll find is this is not going to be possible, and this is going to be possible, and then this is not going to be possible, and the last 3 will be possible. So I have effectively how many that turned out to be possible in this case? 1, 2, 3, 4, 5. 5 out of 8 are possible states of the system. Now, here's the thing. If you take these 5 guys and write them as a DNF, that is, you go and say, let me pick the first guy. The first guy says, okay, 1 and okay, 2 and not okay, 3. Or, and then you pick up the second guy and you say, what is that guy saying? Okay, 1 and not okay, 2 and not okay, 3. And you do the other 3 guys, right? So there is one more, and one more. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And each one of these guys, we called it a diagnosis. That is a state of the system that is compatible with the system description and system observation. What are you going to get? That is going to be equivalent to what one of you wrote, which is the fact that not okay 3 or not okay 1 and not okay 2, right? And this is what we call the health condition given a system description and observation. So the notion of a health condition is defined for a particular system description and a particular observation. This is the systematic way of getting this guy, which we also notated by health of delta and alpha, right? One of you just did it intuitively, but if you go and systematically check every possible state of the system and collect those that are compatible with the observation and system description, take their observation, you get back your formula in that particular case. All right? Now, the question that I have for you is there a way to get to this more compactly, right? So in this case, we did it the hard way. There is actually a tool that we studied which allows us to actually get the same concept, the same formula, without doing this enumeration. There is a compact way in which we can describe this. You want to think of this guy here as being effectively what I can conclude about the health variables. What tool did I use to say, tell me, what does your knowledge base say about a particular set of variables, right? That was the notion of projection or the notion of existential quantification. So in this particular case, if you have this guy, which is delta B, and you go ahead and add to this the observation that I have not A and not B and E, so that is what I know. I know the following. I added to the system description. If you go ahead and say, well, what does this tell me about OK1, OK2, and OK3? That will end up being this guy. Now, how do we get this? We get this by existentially quantifying all other variables. So if I existentially quantify the variable A, the variable B, the variable C, and D and E from this, what am I doing here? I'm taking my system description, adding the observation, and existentially quantifying all of these variables. That means I am projecting on what? I'm projecting on a K1 or K2 or K3. This would be all that I can conclude about these particular variables. And if you do this in this particular case, you will end up basically getting this expression here. So what you need to do is effectively do projection, and that will have implications. Let's do a very quick example so that you see this in the working, because you do have a simple tool that you can use to do projection, and we will use it actually to do this particular example, and then we will tie to prime implicate and prime implicants and tell you some more things there. So in this example that we're going to see next, and let me see, I can clear these things, I believe. And we're going to look at this guy. And in this guy, the system description is delta A. And the system observation we are going to use in this particular case, it's simply going to be A and not C. So this is high and this is low. We already concluded that this is basically an abnormal observation. Intuitively, I ask you a question about this of what went wrong. If I want to ask you what went wrong here, and that is what's the health condition of delta A and alpha, what would you write here? Okay, what's the intuition? What can you conclude about this guy in this case? What went wrong? What can I say in this case? All right, this is the system. This was high and this was low. The only thing I can say in this case, excellent. Someone said, all I can say is not okay one or not okay two. That's pretty much what I can say. One of them broke. Well, you know, the tool and the claim now is if you take delta A and conjoin it with this alpha and then existentially quantify the variables A, B, C, the claim is this will end up being not okay one or not okay two. And let's see it. We know how to do this, right? One way for systematically computing these kind of expressions is to use directed resolution. So if we use directed resolution, you just want to make sure that when you order your variables, you want to put these two guys last, right? So I have A, B, C, and these are all of my variables. I build the buckets this way where I put these first and I put these two guys very last. And then I do, directed resolution. And what I end up getting basically in the last two buckets will be the projection on these two variables. Let's do it. If you convert this to CNF, you end up getting the following clauses. I'm going to just, because we know how to do this, I'm just going to put them basically here in their corresponding buckets. There is not much difficult in doing this, given that we know how to do it. So I'm going to put the system description first. And this is going to be not OK2, not B, not C. And finally, here I'm going to have not OK2 and B and C. So there will be 4 clauses actually generated by this system description. Again, not OK1, not A. This should be not B here. And not OK1, A, B. And then I'm going to get not OK2, not B, not C. And then this is basically not OK to BC. These are going to be the clauses that come from the system description. But I also need to add the system observation. The system observation is 2 unit clauses. The first one end up appearing in this bucket, and the second one not C ends up appearing in this bucket. Okay. And now if you go ahead and do directed resolution, what you're going to find is, let's see, what can I do here? Can I resolve this with that? No, I get a trivial clause that contains both of these. Can I resolve this with that? Yes, if I resolve this with that, I will get not OK1 and not B, and this ends up actually going here. So I will end up getting not OK1 and not B. Okay, this is resolving this guy with that guy. And that's where it looks. And then I go to the second bucket. And I can resolve this with that. No, will not resolve. I can just, so let's see, this with that will not resolve, because even though I have B and B, I'm going to get a trivial clause, but I can resolve these two guys, right? I can remove this with that. And in that case, I'm going to get another clause that says not OK1, comma, not OK2, and C. Okay, so I resolve these two guys over B. And then I get not OK1, not OK2, and C. So here I am. And this is the only thing that you can do at this bucket. Then you move to this bucket and you resolve over C. And what do you get? You get not OK1, not OK2. All right, and we're done. So what happened here? We went and did directed resolution. I made the wrong line. And we projected on these two variables here. And that basically gave me this guy. And that is exactly this guy. Okay. So what we did is simply projected on the health variables. This tool was not available when people developed the notion of model-based diagnosis initially. What they did is, and I'll tell you now, and that brings the connection of these notions of prime implicant and prime implicant. So the main question we're going to focus on is, fine, I got it. The central notion here is that notion of health, or the health condition for a particular system description and observation. And you just told me how to do that, right? Take the conjunction and existentially quantify every variable but the health variables. That's the guy. And it's a Boolean formula. And the question is, what do I do with that guy? In the simple situation we've seen, it was a very simple Boolean expression. When you look at it, you say, okay, I saw what happened, right? I got what happened. That is, When I came and told you not okay 3 or not okay 1 and not okay 2, it was very obvious. But suppose that you have 100 components and I give you that expression and it's like this huge formula. And I say, this is what happened. This is the formula. What do you do with that? Right? And it turns out that you can do a number of things. And we're going to go over some of them now. And depending on what you want to do, you would want to represent this Boolean formula in a different way. Now, we spent a lot of time talking about how do you represent Boolean formulas. We talked about CNF, we talked about DNF, we talked about circuits, and it turns out, depending on what you want to do next, as a result of asking the question, what happened, the different form will be suggested. And when people initially developed this, they suggested prime implicant representations of these things and prime implicate representations. Now, they did not call them that. They call them other names. So on the next slide, I'm going to show you if you take the health condition and represented in a prime implicant form, what do you get according to the terminology of diagnosis? And if you represent it in a prime implicate form, what do you get, right? And that should be very quick. It's just a terminology. But then we will argue that typically you don't want to do this or that, but you may want to do some other representation of the health condition, in particularly some of the tractable circuits that we had. So what we'll do is we'll end by telling you what do you gain or what things you can do from a diagnosis point of view if you, for example, were to represent the health condition as a DNF circuit. Okay, there is a major operation that people are interested in diagnosis. Neither of these will support, and this guy will support easily, and this guy will support it in polytime. So we really have two major things to talk about in the next 12 minutes or so. Here's the thing. We have the health condition of some system description and observation. Okay, what people defined is the notion of a conflict and define the notion of a minimum conflict and define the notion of a partial diagnosis and define the notion of a kernel diagnosis. Now, I'm not going to give you the definitions of these because we know what they correspond to now. But if you look in your chapter, you're going to see how people define these guys. I'm just going to tell you what they are given what we know now. A conflict ends up being nothing but a prime implicate of this guy. Sorry, this is actually should be implicates, not prime implicates. So implicates of, and the minimum conflict is what you would expect. It's the prime implicate. And you can guess what the other guy. What they call the partial diagnosis is an implicant. And what they call the kernel diagnosis is just a prime implicant. Okay? So in a sense, these notions, and you'll see a lot of examples for them in your chapter, are nothing but a rewrite of the health condition in a particular form. The health condition characterizes what really happened, but is silent on the syntax. It just gives you the logical content of what happened. And if you go and write it as a set of prime implicates, you end up getting what people in diagnosis called minimum conflicts. And if you write it as a set of prime implicants, you get what people call kernel diagnosis. Now, intuitively, what is the intuition behind these guys in the diagnosis context? When we did this example, and one of you guys said, let's go ahead and say not okay 3 or not okay 1, and not okay too. That was the health condition in that case. What form is this? This is a DNF in this case, right? And if you look at these guys, you will find that each one of them is a prime implicant in this particular case. So this is what people will call the kernel diagnosis. So this is a kernel diagnosis, and this is similarly a kernel diagnosis, right? This is a particular form, okay? Now, you can write this in another form. You could have written this as not okay 1 or not okay 2, sorry, 3, and not okay 2 or not okay 3. You guys agree with this? This guy broke together with this, or this guy broke together with that. These are equivalent. Now, this was a DNF, this is a CNF. I'm writing the same logical condition in two different ways. And just like this was a prime implicant form, that each one of these are prime implicants, in this case, it ends up being that these guys are actually prime implicates. So this is what people would call a min conflict, and they will call this a min conflict as well. Intuitively, there are different ways of communicating what went wrong, right? This form is saying, look, one of these must have been broken, and one of these must have been broken, and. So each part of this is picking a subset of the components and saying one of them broke. And moreover, it's a minimal. That is, you cannot make it any shorter. This is this guy. This guy is picking up specific combinations of components and said, this is an explanation. One way to explain this is to say that this guy broke. That will explain the situation. And here's another explanation, that these two guys both broke, all right? Again, the way we did it now is we looked at the health condition as a Boolean formula that we obtained through existential quantification, and we said these just happen to be two syntactic forms of that which have different roles. You may like this or may like that. People typically would find this more suitable in this particular case. But you actually don't even have to have either this form or that form. You can represent that particular health condition in other ways. And I'm just gonna end here by showing you another way to represent this and why that may be useful, all right? And it will tie to something that we talked about before. But I hope now what's going on, you know what's going on. The fundamental notion is this notion of a health condition, which is you take your system description and system observation and project on the health variables. But that's a logical condition. And then you have to ask yourself, how do I represent this syntactically? Is it as in a prime implicant form, or is it in prime implicate form? And those forms end up corresponding to names people introduced in diagnoses. And then again, it depends on what you want to do with this later. The one thing I want to show you quickly, because this is pretty important, is the fact that this notion of minimum cardinality diagnosis. So minimum cardinality diagnosis is that I'm just not interested in all possible states of the system that are consistent. So what I have is, let's say in this example we were looking at, I have OK1 and I have OK2 and I have OK3. And if you look at the possible states of the system that were actually consistent with my observation, as we discussed, there was 5 of them. So this is one, the second. These should have been the 5 different ways or the 5 different states that the system can be in. Now, there is this notion of a cardinality, which we talked about before. Let me count how many broken components, right? In this case, I have 1 broken component. In this case, I have 2. In this case, I have 2. In this case, I have 2. In this case, I have 3. Okay? So not all states are equal from that point of view. Different states imply a different number of false. And what people are interested in is, I want those states that have the smallest number of false. And we call these min cardinality diagnoses. Okay, so in this case, there's only one of them. This is the guy that says only one component broke. This guy says 2, 2, 2, and 3. So given the health condition, I'm interested in finding only those states characterized by it which have minimum cardinality. Well, we have a tool to do this. We discussed it before, right? If your health condition is in DNF form, then you can actually do minimum cardinality computations in linear time on the DNF. So one reason that you want to compile or represent your health condition as a DNF circuit is then you can compute minimum cardinality diagnosis easily. And we've seen examples of that. And in your chapter, you're going to find a detailed example of what we did earlier, but in the context of these examples. And that's pretty much what I wanted to say today. We took a little bit extra time, maybe not a lot, but again, that concludes our discussion on diagnosis here. Your chapter has a lot more material, but we will stick to just what we covered here. So thank you again, and I will see you next week. Thank you.